Hi everyone, and welcome to this webinar on what's new in PTV Vissim and Viswalk 11. I'm Alastair Evanson, Solution Director for PTV Vissim here at PTV Group, and I'll be joined today on the webinar by my colleague Jochen Lohmiller, who is the manager of the product management team here at PTV headquarters. So in this webinar, we're going to demonstrate the new functionality that we have provided in the most recent release of Vissim 11 and Viswalk 11. And we're going to cover a range of the different features from simulating autonomous vehicles to new options for routing vehicles and pedestrians, some of the extensions that we've introduced for managed lanes, as well as a selection of visualization features. We'll then move on to some new features that we've developed to enhance the integration with PTV Visum, so for those of you who undertake multi-resolution modeling. And then finally, we'll go through some of the usability enhancements that we have and finish up with new features that we have in PTV Viswalk. So just before we start, there is some technical information that I'd like to run through on the webinar. So all of the attendees are not able to use your microphones, but you are free to post comments and questions in the question window on the chat. And myself and Jochen will try to respond to your questions during the webinar. After the webinar, we will both be available for some time to answer further questions via the questions window as well. We are recording the webinar and it will be made available to you shortly. So we're going to host it up on our YouTube channel, and therefore you'll be able to get back to it at any time and look at some of the features that we've presented if you'd like a little bit of a refresher as well. Okay, so now I'm going to hand over to Jochen, who is going to move through the new features for autonomous vehicles.
Hello everyone from my side. So we were participating, or we still participate in a research project called Coexist, and this research project is all about making cities, local authorities, transport planners able to answer some questions which come up in this transition from conventional vehicles to connected and autonomous vehicles. So how can you model connected and autonomous vehicles? Our part in this research project is to extend micro and macroscopic modeling tools to enable these scenario analysis for the coexistence of conventional vehicles and autonomous vehicles in the network. So what did we do? So we came up with an calibrated connected autonomous vehicles driving behavior model, and the input for this calibration was mainly from a prototype testing, which we did on a research on a test track, and we had here this test track scenario. So there were one human driver leading and two autonomous vehicles following. There were different cases tested, like different headways, if connectivity was switched off or switched on, and we observed exactly the behavior of these current prototypes of connected and autonomous vehicles. And what you see here in the chart is one result. So here you see the difference in velocity between the two autonomous vehicles and also the distance between the two vehicles. So meaning here in red speed, the vehicles are driving at a speed of around 120 kilometers, and when connectivity is switched on, they have a distance between each other of 14 meters. The distance is not exactly fixed, but it's almost fixed, so there's almost no variation in delta velocity, difference in speed. If there is no connectivity between the two vehicles, we see that there is a higher distance kept. So they go from 14 meters in connectivity to like 38 meters when they are not connected, only automated. And also here, when they are not connected and they don't get the information from the leading vehicle what it's doing, we see also a little higher distribution of speed compared to this one. So this is basically what we observed. And one fundamental relation what we also observed is if you look at the vehicle speed on the x-axis here over the distance to the vehicle in front. And we see with increasing vehicle speed, the vehicles, they keep larger distance, even in connectivity, but also, and this is the case here for non-connectivity. Again, 120 leads around to 48 kilometers per hour. But the interesting thing is we see this linear increase here, and also there's no real distribution in it. It's many cases up and down, different speeds, but we don't see a lot of distributions on it. And for those of you who are very familiar with Vissim, the linear relation between speed and distance between the two vehicles, this is replicated in Wiedemann 99. But how does the default look in Vissim? So the default look more like this. So there's highly stochastic variation in car following behavior in our default values. So this is just because there's this oscillation when following, there is the imperfect control of braking pedal and throttle, and so on and so on. So, and what we try to achieve is to calibrate through parameter changes, but also to improvements in functionality, to calibrate it so that it looks almost the same. And this was a current stage which we achieved by calibrating PTV Vissim. And I'll now explain you what were the functionality which we introduced to model connected and non-autonomous vehicles. First, I would like to mention that in the defaults of PTV Vissim 11, there are 3 new driving behaviors. They are called a cautious driving logic, AV cautious, as you see here, AV normal, and AV all-knowing. So the cautious is driving, they keep a larger headway compared to human driver today. You see this in the difference between the red vehicles, which are the cautious, which make use of the cautious AV driving logic, compared to the urban, the default in Vissim. And we see here also a smaller throughput for this. So they try very carefully and follow the so-called brick wall distance, which I explain in the next slide. Normal driver logic is they behave similar to human behaviors in terms of distances, what they keep to each other, but we reduce all the stochastic, which is the case for all 3 autonomous vehicles behavior. So there's no much variance in the car following behavior. The all-knowing driver logic is a little bit more aggressive driving behavior. The assumption is that they know about all the surrounding vehicles, they detect everything, and they optimize their path to their destination, also making other vehicles needing to react to their behavior. The all-knowing driver logic is also the only one which adjusts their headway when another all-knowing vehicle is in front of it, because the assumption is that they are connected because they know of each other, and then they can use smaller headways. So what are the new functionalities in the driving behavior in PTV Vissim 11? First one is enforced absolute braking distance. So this is for the cautious driving logic, but you can activate it for any driving behavior in PTV Vissim. This means, so a vehicle always keeps a safety distance between the 2 vehicles, so that even if the vehicle driving at a certain speed, for example 100 km, this vehicle always makes sure that if this vehicle would immediately be a brick wall, meaning speed 0, it still is able to make an emergency braking so that it can stop in between, leading, of course, especially at higher speed, to very high safety distance, and then of course you get much less throughput. The other change which we did is the number of interaction vehicles. In previous version that was just one interaction parameter, and it was the interaction vehicles, which also made use of objects. So in interaction vehicles there were also like signal heads or reduced speed areas included. So now we splitted that in vehicles and objects, and the reason is that, or let me first give an example how it is currently modeled. So if the interaction objects is 4, it sees a maximum of 4 vehicles or objects. So 1, 2, 3, 4. It doesn't see the fourth vehicle, even though in direction vehicles is set to 4, but this is also considered as an object. The maximum objects is 4. So now the reason why we implement it is that, for example, autonomous vehicles with a specific sensor may not be able to see only the leading vehicle and not other vehicles, because it can't see through other vehicles. So that's why you can limit, for example, the interaction vehicle to 1. And what happens then, it only sees one vehicle, but because of interaction objects is 4, it still can see other objects which are behind or further downstream. Meaning this vehicle can react to the leading vehicle, but it can also get, maybe because of connectivity or something, it can get the information from the signal in order to react to it. Another functionality which we introduced is the headway based on class of leading vehicle. This means if we have a connected vehicle, for example, and this is following another connected vehicle, and we have seen this in the test track as well, they can go down to very small headways, distances in between the two cars. So if we have this case that both are connected, they can follow each other in very small headways. But if an automated vehicle in front is not connected, so this vehicle does not get the information immediately through connectivity, what it will do, then they need to keep a higher distance. And also you could assume, okay, if I'm following a human driver, I even need to take more safety distance when following. So how can you model that in Vissim? So there's a new driving behavior, following behavior depending on the vehicle class of the leading vehicle. So you can specify for a driving behavior if the vehicle follows a vehicle of class car, which could be a human car, then use this following parameter. And if I follow another all-knowing, so this is the driving behavior all-knowing, then I can go down to a very low value here, for example, in VDMA 99 CC1 0.6 compared to 2 seconds when following another human vehicle. And this option is available not only for autonomous vehicles, but in general. So you can make use of it, for example, if you want a vehicle following in different distances to another car compared to a truck, for example, that you normally keep a higher headway to a truck. The other option is the implicit stochastic. So within the car following logic, there were still stochastics which you could not influence in the driving parameter. So, but now this option, you can switch it on so that all vehicles in Vissim 11 with the same driving behavior will react exactly the same if they have the same situation. This was not guaranteed in earlier version. We have introduced an increased acceleration. This is because when following and if the leading vehicle is accelerating, then the following vehicle in PTV Vissim is reacting a little bit too slow. But if you have connectivity, they could even accelerate both with a similar acceleration. And to model that, you can increase the percentage when accelerating for the driving behavior. And then a very simple one for occupancy, you can have also occupancy 0. Before the lower limit was 1 in occupancy. So now having this default driving behavior allows then cities, transport planners to make use of what is currently available in prototype. And you could test different scenarios. What if we introduce autonomous vehicles in there? Of course, with these default values, we have some specific values set, for example, for how they will follow each other, in which time gap or distance they will keep. But these are also from our side currently only assumptions. So if you make your own study, you should do the research and you should come up and justify your assumptions in your project.
Okay, the next feature that we'd like to run through is attribute and formula-based routing. And this really looks at how we can better control the vehicles and pedestrians within our simulation as well. So I'll just quickly run through the first one being attribute decisions. Now, what this allows us to do is actually change that attribute or add an attribute to any pedestrian or vehicle while the simulation is running. So you'll find this feature under the network editor. It's a new network object. And once we put that network object onto the simulation, we can change some of the properties of vehicles and pedestrians in the simulation. So here you can see that as pedestrians enter the network, they're white, so they don't have an attribute assigned to them. We then have an attribute decision point where these pedestrians are walking past a certain point, and then we're giving them an attribute of maybe who wants to go and buy a magazine or a newspaper, who wants to go and get some food, who needs to go and buy a ticket. And we could extend that to who is running late for a train and needs to get to a platform in a rush. Lots of different use cases related to pedestrians. And then we can control what those pedestrians do in the simulation based on the attributes that they have. And I'll run on to that in the next slide. If we look at a vehicle example, this can then also be applied to things like vehicle occupancy. So we can add up distributions that show the vehicle occupancy, change that occupancy as a vehicle's in the simulation. We could change some of the speeds, the driving behaviors, lots of different attributes related to it. A follow-on of that feature is that we have something called formula-based routing now. And this will allow us to actually route pedestrians and vehicles in the network depending on those attributes. So here we've just got a simple model that shows a doorway with a low height to it. And what we have is pedestrians who have a height under 1.65. So those people who have an attribute of their height. If they're under a certain height, they can walk through the doorway. If they're over a certain height, they have to walk around the doorway. So this is how we can actually take those attributes decisions and then make routing based on the attributes of those pedestrians. Now for vehicles, I'll just quickly run through an example within Vissim that we have. So here we have quite a simple model that has been set up, and within this model we have 5 different destinations, and we have numbers of vehicles that come into the network and route to those different destinations. Now, as these vehicles enter the simulation, we can see that these vehicles have an undefined destination. So currently, when we look in our quick view, we can see under destination it's blank, and that vehicle is showing as black. Now, as we cycle through and that vehicle hits an attribute decision that we've assigned here, we've given that attribute decision a distribution. So here we can see the new vehicle attribute decision, which is accessed through the network object. We've put it onto our link structure, and then we need to define it. So here we've given a distribution to it. And that distribution is our 5 different destinations, and then we can apply 10% to destination 1, 50% to 5, and so on and so on. We can also add empirical numbers here as well. We don't have to use a distribution, so if we want to give a single value to vehicles, then we can do that as well. So, for example, all vehicles traveling across that point get an occupancy of 4 people, for instance. So now that our vehicle crosses that attribute decision, we can see that it changes color, and it now goes to blue, and its destination is number 4. So when we select it, we can see it has destination 4. Now, we want to make sure that that vehicle is traveling to that area. So upstream of our vehicle attribute decision, we actually have a static route decision. And now if we look at our static route decision, we have different options for route choice methods. We have what you will be used to is using the static route choice method, but we now have this addition of having a formula-based route choice method. And what that means is that we can choose some of those attributes and actually allocate a route through the network based on what that vehicle attribute is. So here I just have a very simple formula that looks at the destination, and if the destination is under 3, the vehicles turn left so that they can access these 3, and if it is over 4, they turn right and access the others. Now, when I cycle these through and that vehicle goes past that routing decision, I'm also then able to change those attributes again. So here, Now, if we actually said that we wanted to change this vehicle, make its destination to, it can continue on that route for a certain point, and then it will flick back and take the alternative route in order to get to 2 as well. So these are, we can have a succession of formula-based routes that allow us to make multiple decisions about how those vehicles or pedestrians are treated in the network. And we can also change those attributes multiple times throughout the simulation as well. So it really gives you a lot of power in how you can start to allocate and control vehicles during the simulation run as well. Okay, and if we look at some of those different use cases, and we extend that, for instance, we could look at things like toll booth operations where we want to allocate certain vehicles to certain lanes based on their attribute. So the attribute could be I'm paying by card, I'm paying by an e-tag, I'm paying by cash and I want change, I'm paying by cash so I have the correct change. Those types of attributes can be added to the vehicle and then the vehicle routed. Likewise, it has a very strong application in pick-up and drop-off. So if we think of an airport example where we have different doors allocated to different flights and certain airlines, being able to give vehicles an attribute of an airline name and making sure that that vehicle routes to there. Likewise, for rideshare pick-up and drop-off, when we want to allocate rideshare pick-up and drop-off in certain areas along certain curb frontages, again, attribute decision to allocate that vehicle to be a private vehicle or a rideshare vehicle, and then a routing, a formula-based route that specifies exactly where that vehicle gets to along the curb. Okay, the next feature I wanted to run through is the implementation of managed lanes in dynamic traffic assignment. So for those of you who use the managed lanes function, this is obviously where we have the local decision whether to use a general purpose lane or a managed lane, and that decision is made on various kind of coefficients based on the journey time saving that people will get from using that HOV or managed lane. We've now expanded this application so that it works with dynamic traffic assignment, and that means that we can actually assess the attractiveness of that managed lane corridor against the attractiveness of parallel wider routes as well. So if we think about particular use cases, this could be we want to see the redistribution of traffic from parallel corridors onto a managed lane if a managed lane was implemented. Likewise, if there is any reallocation of traffic away from a managed lane onto parallel corridors as well, and maybe making the traffic situation on parallel corridors either better or worse. So this allows us then to evaluate the capacity of managed lanes for future demand, but also evaluate the impact of potentially changes to managed lane pricing on the surrounding network, some of the sensitivities of vehicles maybe reallocating from that managed lane corridor onto wider alternative routes as well. So something for those of you who do a lot of managed lane modelling and toll modelling, being able to assess a wider area and wider network is something you can do with Vissim 11. Okay, now I'd like to run through some visualization features. We've been working quite hard to improve visualizations within Vissim. One of the features that we've implemented is that we have 2D labels on vehicles now. So here, when we tick label visibility, you can see here I'm showing vehicle speed, but we can change potentially to lots of different attributes. Down here to select delay time, I can now see the delay time of every vehicle in every time step in that model. I can change the font size of that label. I can change the color, the number of decimal places, just really being able for you to get a live feed of information and data about the operation of certain vehicles in the network whilst the simulation is running. So something that's quite useful, but has a wide range of applications as well. Similar to the 2D information, we also have 3D info signs. These are free text signs that you can add into the network at any point. Again, they're a network object. So you can put a sign above an intersection, for example, to demonstrate the intersection name. If you were creating a fly-through video and you wanted to provide some context for that, you could add the level of service or the average delay at that junction, again to share some kind of information. And on an individual vehicle, we can also attach info signs as well. So as vehicles are moving through the network, we can have a 3D sign, as you can see in the picture on the screen now. Okay, the next visualization feature is that we have now included a visualization for queue lengths. So this means that graphically within the network editor and on links, we can see the extent of a queue length for each time interval of the evaluation. And this relates to queue counters and node evaluation as well. And we can change different attributes, so we can have it by queue length color, we can have it as a queue length max and average, and we also get labels as well to actually provide the empirical data that shows the exact length of the queue. And where we do have nodes and we have queues that extend beyond the back of the nodes, we also get a spike to demonstrate that that queue is continuing through that node. And here we can see it's followed up by another queue counter that demonstrates the extension of that queue. So how we access that in the network editor, when we are running an evaluation with queue counters, we can go and tick show queue lengths, select queue length or queue length maximum, current time interval, click OK. And now that is activated in the simulation, and you can see here that we're already showing the max queue length for the time interval of the evaluation on the network editor. We can then go in and change the color of that. So if we don't want it to be blue, we maybe want it to stand out as red. We can change all of the graphic parameters again as the simulation is running, and this will update through each time interval that you've set up for your evaluation as well. So if your evaluation runs for 5-minute time intervals, then that's what the data will be presented for as well. Okay, the last feature I wanted to run through on visualization is that we now have the ability to change name network layouts by keyframe. So when we're setting up AV recordings, we can actually set different network editor layouts and define them to keyframes. So that means that we can display a lot of different information, like you're seeing here on the video, related to number of pedestrians in the network, or related to experience delay or level of service, or all of the different evaluations that we want to show. We can set each of those evaluations up as a named network layout, and then we can define those through keyframes so that when you create that AV recording, like you see now, you get a real storyboard of cycling through each of those keyframes automatically within the AVI recording. And that allows us really to present a lot better where we have large complex schemes and we want to present through videos lots of different information within certain times. This allows us to create quite a clean video with a nice story of how you can cycle through and present that data as well. Okay, the next feature I'd like to run through is how we've improved integration with Visum. And the way that we've done this is actually for being able to share assignment results and routing from Visum into Vissim, even if the network objects and the networks themselves have been created independently. So here I have a basic network that I've imported from Visum through the ANM, but currently we don't have any routing set up. So we've just imported the link structures through ANM, and when I go to my static routes, we can see that they're blank. The feature that we now have is that we have the ability to import a route coordinate file. So here I've taken from Visum a route coordinate file. I can import it as a static or dynamic route, and that brings the information from Visum and now snaps it to my Vissim network. So here I can see my routes are now there. If I was looking at this and I decide that I don't like the geometry of a certain intersection, it might be that this has come from the macro model and there's an error in the coding in the macro model. I want to fix this so it is a better representation in my micro model. So maybe changing some lanes, adding connectors, just making sure that that geometry is a lot cleaner for a micro application. So here I can make those changes. And now when I actually run the simulation, I can see that I have some errors because I changed that network structure. So here we can see that some of those static routes are not complete. Now, previously we would have had to make a change in the visual model and re-export the route. Now, all that we need to do is just re-import that route coordinate file. Because it sits independent from the link structure and is coordinate based, it snaps to those changes that I've made in the network. And by re-importing it, I now have all of my straight on and left turn movements at that intersection automatically snapped to that new link structure that I've now implemented. So the stepped process of having to go between Visum and Vissim is a lot quicker now and a lot simpler. And it allows us to be able to develop both Visum and Vissim models independently with independent network structures, but still be able to share assignment results and routing between the two. So it's really powerful feature for those of you who work within different resolutions of modeling from macro down to micro as well.
Now, I'll talk about some usability feature to help you to work quicker and easier within Vissim. The first one is we introduced filters for lists. As you probably know from Excel or from Microsoft Access, very similar now you have the list filters in Vissim. If you click here on the top on the header of an attribute, you can activate a filter. And the filter is depending on the data value. So if it's, for example, a text, you can filter for contains a specific letter sequence, or it starts with or ends with. If you filter a number, you can filter higher than, lower than. You can even filter colors to specific values or something like that. Or as in this case, filter a vehicle type, and then it lists the available vehicle types, and you simply clicks to the one you want to have it equal. And then the list is filtered. It shows you here. It shows currently only 8 of 138 objects. And of course, as all the list configuration, if you save your current list view in the named list layout, you can also save the filter. And easily then, if you have saved different layouts, you can switch between the different layouts, what attributes to be shown and so on, but also which filter should be applied and which not. We think a very useful feature. Another feature which was wished for a very long time is the measuring tape. So you simply click in your network editor on the measuring tape, and you can measure the connection between 2 points. You can measure along a link sequence, a link route, and it gives you the numbers also for individual values. The other feature is the quick info. It can be activated in the user preference network editor. By default, it's switched on. And if you hover through your network, you see on the lower right to your mouse cursor some information, like which network object it is, what's the network object number, or even when you create or edit, you get additional information as you've just seen with the link length. And if you create an area, for example, it shows you also the length of active edges. So instead of having to click onto a network object to see in the quick view the number and some attributes, you already have them live while hovering through the network, which might be useful. A smaller improvement, but sometimes very efficient, is that if you enter a number in a drop-down menu, so in this case you're looking for a specific signal head, and if you would enter 137 in Vissim 10, you enter at the number 7 somewhere, because it only remembers one number. So if you now enter 137 quite quickly, you end up at 173 to just select the specific value. So this is not only available for signal head, but for every drop-down list in Vissim. Another bigger improvement is in the attribute selection dialog. So whenever you need to configure, for example, your list, or you select which attributes to be shown in your quick view, a new dialog will open. And there's new functionality. The best one, from my perspective, is the search for attribute name. So if you can just enter any letter sequence, and it filters automatically and shows only the attributes which contain this letter sequence. Then you can select between alphabetical order or semantic sorting. You can directly create the user-defined attributes for this network object. Also for aliases, so you can add, edit, or delete aliases directly from there. You can make a simple view, hide some columns, or extend them. Also adding like a group of attributes. So as an example, all user attributes to be added to the right-hand side, to the list. You show also on the left-hand side by this selected option which attributes are already on the right-hand side list. And additionally, multi-selection is now possible by either holding the Shift key or the Control key to multi-select. Another feature is circular shaped areas. So if you want to create circular areas, you simply have now the option to select circular area, and if you create one, it will open the circular area. And here you see also the quick info, but with an extension. This blue rectangle identifies that you can edit this number. So if you now, while adding this area, simply enter a number, it will automatically adjust the radius to the specific value you have just entered. Okay, that's for usability. Let's come now to the pedestrian functionality, which we have in PTV Viswalk 11. So the first one, also on visualization side, is we have now 3D pedestrian models with luggage. As you can see them here, I need to remember there's no specific behavior, different behavior for them. It's just visualization, but that was desired specifically when you model stations with PTV Viswalk. The other functionality is to model the interaction between vehicles and pedestrians much better. And as you see here, pedestrians crossing from the north a road, this runs quite quick, but showing that in the new functionality, which is on top, the pedestrians are able to walk around the vehicles, so to adjust their routing to their destination to work around. And if we see them standing on the lower end, they walk towards the vehicle and stand and wait until the vehicle disappears to continue the walking. So now they see, they calculate in their route calculation, they know exactly where the vehicles are, and they adjust their path to walk around of the vehicle, which helps you if you want to model pedestrians crossing in a shared space environment even better than before. Also, a better navigation is when pedestrians walk towards their waiting position on a waiting area. Previously, they were not able to see obstacles. That saved, of course, in performance, because it's much quicker to calculate to go on the direct path. But of course, if you have obstacles on your waiting area, then pedestrians were stuck on these obstacles. The same is also activated when pedestrians board public transport vehicles. Then they now are also able to see obstacles and walking around towards the door for boarding. For stairs, there's an improvement. So it's now much easier to model like different shaped stairs as you see them here. Straight with landing, angle with 90-degree landing, U-turn stairs, and so on. So therefore, in ramp and stairs, you have some additional flight attributes which you can change. And then you can have this as one network object with different 90-degree values and so on. So they are all compatible to the standard from BIM, Building Information Model. So if you import a model from a BIM standard, it will create these new stairs automatically. On ramps, not only stairs, but also on ramps, it's now possible to activate the dynamic potential. The dynamic potential makes it pedestrians react more realistically on other pedestrians. As we can see, if on the left-hand side, where the dynamic potential is not switched on, they have much more conflicts and between the pedestrians coming from the north and pedestrians going up from the south. If the dynamic potential is activated, they avoid these conflicts more efficiently, and even more if the keep right is activated. So pedestrians try to keep right on the ramp, in the stairs in this case. So it gives you a better simulation for pedestrian. Again, dynamic potential is needs a lot of resources to calculate. So simulation speed is going down while activated it. So we recommend only using the dynamic potential when you need it, or at least for your last step if you run the results on your simulations. Another more simplistic way of modeling a specific behavior for pedestrian is that you can have now a walking speed factor for an area. If you just imagine you're walking in a building and then you go outside and walking into another building, but it's heavily raining. And what you can observe in the people that when they exit the building, they accelerate, they go faster in order to arrive in another building quick. And this is what we can see here. And you can model this now more easy if you just add a speed factor to this area, and then the pedestrians will adjust their speed while walking on this specific area. So coming to the end of this webinar, we hope we had some attractive features for you, usability, visibility, autonomous vehicles, pedestrians, wherever you're working on. I want to mention PTV Vissim 11 is already available, so you can start using the feature and observing themselves. In addition to the features, there is new example models available, as the one you can just see with the cable cars. So we are looking forward to hearing your feedback, and we very much appreciate all your further feature requests from you. Additional material on what's new in Vissim and also other information can be found on our website and on our YouTube channel, where we will upload this webinar as well. Should you have any more questions, you can still ask them using the questions window. I need to admit, it might take a little bit for me to answer the question, but we'll still stay a while here to answer your questions. For those of you leaving right now, all the best to you, and enjoy modeling with PTV Vissim.